This PowerPoint presentation covers section 16.3 from our textbook on the second and third laws of thermodynamics. Before watching this video, make sure that you have completed the reading guide section 16.3. Also have a copy of your chapter 16 handouts ready to take notes on. We've previously seen that entropy is a state function that is tied to probability and the spontaneity of physical and chemical processes. Let's explore that further and introduce two new thermodynamic laws. Recall that in thermodynamics, we tend to talk about the energy changes for a system and the surroundings. The system plus all of its surroundings constitute the universe. So we can say that the delta S for the universe is equal to the delta S for the system plus the delta S for the surroundings. Further, since delta S can be determined by Q reversible over T, we can write the following for delta S system and delta S surroundings, where Q reversible is the heat transfer between the system and surroundings. So Q reversible for the system will be equal to minus Q reversible for the surroundings. If the system is hotter than the surroundings, there will be heat flow out of the system to the surroundings. And Q reversible will be a negative number. The system loses heat and the surroundings gain heat. This means that delta S for the system will be negative. We've already stated that T for the system is greater than T for the surroundings. That makes delta S system a smaller negative number than delta S surroundings, since T is in the denominator. That means that the sum of delta S system, which is a negative number, and delta S surroundings, which is a positive number, in this case, will be greater than 0, because the negative number is smaller than the positive number. This is a general result and is the basis of the second law of thermodynamics. The second law of thermodynamics states that for any spontaneous process, the delta S of the universe must be greater than 0. If the delta S universe for any process is negative, that process will not be spontaneous, and in fact will be spontaneous in the reverse direction. When the delta S universe is equal to 0, there is no net change and the system is at equilibrium. The second law of thermodynamics states that the entropy of the universe is the quantity that will determine whether a process will be spontaneous or not. So in order to determine whether a process will be spontaneous or not, we need to determine the delta S of the universe, which means that we need to determine the entropy change for the system and the surroundings. Let's start with the surroundings. For a closed system, where no matter is exchanged with the surroundings, we can determine the entropy change for the surroundings by assuming that the only contribution to the surroundings is due to the reversible exchange of heat. This means that for an exothermic process or reaction for the system, the surroundings will gain heat and therefore the surroundings will gain entropy. Exothermic reactions increase the entropy of the surroundings. Delta S surroundings will be greater than 0. On the other hand, for an endothermic process or reaction, the surroundings will transfer heat energy to the system, so Q reversible for the surroundings will be negative, and the surroundings will lose entropy. In this case, delta S surroundings less than 0. Using the equation for delta S to be equal to Q reversible over T, and the definition that Q is equal to delta H at constant pressure, the delta S for the surroundings would be equal to minus delta H for the system divided by the absolute temperature. So the entropy change for the surroundings, the entropy of the surroundings will decrease when delta H of the system is positive, as it is for an endothermic reaction, and the entropy of the surroundings will increase when the delta H of the system is negative, as it is for an exothermic reaction, as we stated above. The third law of thermodynamics states that the entropy of a perfect crystalline substance is zero at 0 Kelvin. This is because there's only one way to arrange the atoms in a perfect crystalline lattice, and if the particles have no kinetic energy, there is no energy to distribute. This means that the number of microstates is 1, and the natural log of 1 is 0, so S will be 0. The third law of thermodynamics is important because it says that we can know the absolute entropy of a system and not just the changes in entropy. This graph shows how the entropy of a sample changes with temperature. At 0 Kelvin, the entropy of the perfect solid is 0. As the temperature increases, the entropy will increase due to the Boltzmann energy distributions. When the temperature is high enough to cause the solid to melt, there is an abrupt increase in the entropy of the sample as the particles gain more freedom and microstates by disrupting their attractions to each other. As the temperature continues to rise, entropy continues to increase, with another abrupt change or increase as the liquid evaporates to the gas phase. Values for absolute entropies of various substances are tabulated in reference tables. In our book, these are found in Appendix G. We define the standard entropy of a substance, S0, to be the entropy of 1 mole of that substance in its standard state at the given temperature, in this case at 298 Kelvin. Notice that the units for entropy are joules per mole Kelvin. Let's highlight 2 examples comparing the entropies of different substances. First, notice that the entropy of methane gas is larger than the entropy of argon gas. This is because methane is a more complicated molecule than argon. Second, notice the entropy for the 2 different forms of water. The entropy of gaseous water is much larger than the entropy of liquid water at the same temperature. This fits with the qualitative guidelines about entropy that we discussed before. To calculate the entropy changes for a chemical reaction, we can use the tabulated standard entropy values from the reactants and products. Delta S naught for the reaction will be equal to the sum of the standard entropy of the products minus the sum of the standard entropy of the reactants, all multiplied by their coefficients in the balanced chemical equation. As an example, let's use the values in the table below to calculate the standard entropy of reaction for the following reactions at 25 degrees Celsius. We'll start with reaction A, which is the reaction of carbon monoxide gas with oxygen to form carbon dioxide gas. Qualitatively, we expect delta S for this reaction to be negative because we are reacting 3 moles of gas to form just 2 moles of gas. Since there's a net loss in moles of gas, we expect the the entropy change to be negative. Putting in the values from the table, we have delta S naught reaction should be equal to 2 times the entropy of the product CO2 minus 2 times the entropy of carbon monoxide and minus the entropy of oxygen. And adding all of those up, we get minus 173 joules per mole Kelvin. Which is in fact a negative number. For reaction B, that reacts 4 moles of ammonia gas with 5 moles of oxygen to make 4 moles of nitrogen monoxide gas and 6 moles of water, we're going from 9 moles of gas to 10 moles of gas, which is an increase in the moles of gas, so we're expecting a positive change in entropy. Delta S naught reaction should be 4 times the entropy of nitrogen monoxide plus 6 times the entropy of gaseous water minus 4 times the entropy of ammonia minus 5 times the entropy of oxygen. And putting all that together, we do in fact get a positive number, 178. .8 joules per mole Kelvin. We've now seen how to calculate the delta S for both the system and surroundings using thermodynamic values that we can find in Appendix G. With those values, we can calculate delta S universe and determine whether or not a reaction is spontaneous. Remember that delta S for the surroundings can be determined from negative delta H system divided by the absolute temperature. If the system is a chemical reaction, then delta S for the system will be the entropy values of the products minus the entropy values for the reactants. And of course, delta S for the universe is the sum of delta S surroundings and delta S system. Combining these together, we see that we can calculate delta S for the universe as minus delta H of the system divided by T plus the delta S for the system. Both delta H system and delta S system can be calculated from values in Appendix G. As an example, let's calculate the delta S universe for the reaction of the combustion of methane shown below. Before we do the calculations, we know that this reaction is spontaneous based on our experience with Bunsen burners. And based on the second law of thermodynamics, we thus expect the entropy change for the universe for this reaction to be positive. I'm going to go ahead and so once again, our goal is to calculate delta S of the universe, which will be equal to negative delta H of the system divided by T plus delta S for the system. And all of these values are going to be calculated as standard states. We can calculate the enthalpy change, the standard enthalpy change for the reaction from the values in the table to the right. Plugging in the values from the table, being careful with the negative signs, and also making sure to include units. We get a value of negative 802.5 kilojoules per mole for the standard enthalpy of reaction for the combustion of methane. This makes sense that it's a negative value. We know that this reaction is exothermic. For the delta S naught of the system, again, we'll use values in the table. It's going to be the sum of the standard entropies of the products minus the standard entropies of the reactants. So we find that the entropy change for the reaction is minus 5.3 joules per mole Kelvin. This reaction has equal moles of gas as products and reactants, so there's no big change in moles of gas. We have a small entropy change here. Putting these together to get the entropy change for the universe, and notice that our units for the enthalpy change were given in kilojoules per mole, whereas the units for entropy are usually joules per mole Kelvin. So we're going to need to convert our entropy value to match the enthalpy value, or vice versa, as long as you make the units the same. And after we do the math, we find that the entropy change for the universe is positive 2.69 kilojoules per mole Kelvin. Since this is a positive number, we do predict this reaction to be spontaneous. Let's review the laws and formulas that we've seen so far. We've talked about 3 different laws of thermodynamics. The first law, energy cannot be created or destroyed, which is another way of saying that the energy of the universe is constant. The second law states that the entropy of the universe increases in spontaneous processes and remains unchanged in equilibrium processes. So the entropy of the universe is increasing. And finally, the third law of thermodynamics, the entropy of a perfect crystalline substance is 0 at 0 Kelvin. We've also seen how to calculate the enthalpy changes for reactions, or the standard enthalpy changes for reactions, based on enthalpies of formation from Appendix G. We can also calculate the entropy changes for reactions based on entropy values from Appendix G. And combining these two ideas, we can calculate delta S for the universe and determine whether a reaction will be spontaneous or not. This slide shows a portion of the table from Appendix G in our textbook. Notice that for each substance, values of standard enthalpies of formation are given in kilojoules per mole. The standard entropies are given in joules per mole Kelvin. Notice also that because of the definitions of standard enthalpies of formation, any substance in the table that is an element in its standard state will have an enthalpy of formation of 0 because it's being formed from its element in its standard state, so there's no net change. However, that same substance will have a positive entropy value because entropies are given as absolutes and are not measured as changes relative to some reference. In the next section of this chapter, we'll also learn about the middle column, which are the standard free energies of formation. You should now be ready to attempt group problems 4 and 5 in chapter 16. In the next video, we'll look at Gibbs free energy.